And now we turn to the end of this Webtalk. On slide 77, we have a so-called Appendix A, where we talk about sample size requirements. And it is the case that when you consider latent transition analysis, you typically need very large samples. You should have at least over 1,000 observations, I think. Because if you want to be studying transition probabilities, you don't want to have too large standard errors to be able to say something specific about them. So a couple of thousand observations preferably. You saw sample sizes that went up to 3,000 and even 5,000, and that's good. Now when it comes to random intercept LTA, I studied the requirements for sample sizes there in a small Monte Carlo simulation study in the second version of the Mutena-Sparahov paper. I looked at latent class indicators that were binary, and I looked at different number of time points. And I found that when you have at least 3 time points, you get good performance at sample sizes of at least 1,000. That is, you get good parameter estimation, not too much bias. You get good standard errors, that is, agreement between the empirical variation in the parameter estimates and the average standard errors, and you get good coverage. But with only 2 time points, you really need more than 4,000 subjects. So in that sense, RI-LTA needs larger samples than regular LTA. Regular LTA can work well with only a couple of hundred observations. Now this is something I studied when I generated the data by each model. So each model is correct. So when I generate a regular LTA model and analyze it by a regular LTA model, it works quite well at much smaller samples than when I generate data by RI-LTA and analyze it by RI-LTA. But that's small comfort for regular LTA, because if data had been generated by RI-LTA, RI-LTA estimates are much better than the regular LTA estimates at sample sizes as low as n equals 500. And we have seen now in several real data analysis that RI-LTA is more likely to have generated the data than regular LTA. And if that's true, then the distortion in regular LTA estimates is bigger than the deficiency of the RI-LTA estimation at sample sizes as low as 500. So RI-LTA is quite practical in terms of realistic sized samples. Now when it comes to decent dynamic structural equation modeling or multi-level time series analysis, Schultzberg and I wrote a paper in 2018 in the SEM journal about the number of subjects and time points that are needed to get good results. So that's a fairly large simulation study with models varying in complexity, varying in the number of random effects that you bring in. And for very minimal models with, say, only random intercepts, the estimation works well when you have at least 10 time points for not too large samples. But if you want to have more random effects, random autoregressive features, random residual variances, you need at least 20 to 50 probably time points. And the more complicated the model is, the more random effects, the higher the requirement on the number of time points. Now when it comes to computing time here, discussed on slide 78, Appendix B, that is the concern that we mentioned earlier, that RI-LTA is considerably slower than regular LTA. So here we have some timings using different Intel CPUs and 4 columns. Here's my current computer, an i7 7700, and I contrasted regular LTA with RI-LTA for that. but we also looked at an i9 computer that my colleague has, and I hope to get soon, using RILTA with 8 processors and RILTA with 12 processors. So for the mood data, which has about 500 observations and only 2 classes, 4 time points, it takes 4 seconds on my current computer using regular LTA. 3 times longer, but still only 12 seconds, so ignorable, using RILTA. But with the dating data, where you have about 3,000 observations, while it takes 41 seconds for regular LTA, it takes 6 minutes for RILTA. Still practical, but if you get an i9 machine, you can do it in 3.5 minutes, almost cutting the time in half. In that case, increasing the number of processors doesn't help much. For the same dating data, bringing in the 4 covariates that are available with this data set, it takes 5 minutes with regular LTA, 40 minutes, 8 times more with RILTA on my current machine. But the i9 machine does it in almost half the time, 21 minutes, and then you get 2 minutes savings by going to 12 processors. Now, Appendix C, the new Mplus features in Mplus version 8.3 and 8.4. I just want to remind you of what they are. 2 versions of Mplus came out in 2019, in the spring and in the fall, 8.3, 8.4. And if you want to catch up on the latest development and additions in Mplus, if you haven't used it in a while, for instance, you can always go to the version history page here, Mplus version history, where we describe carefully the key developments of each release, 8.4, 8.3, all the way down to the first version, Mplus version 1 rather, in November 1998, 22 years ago. So in the last year's Mplus developments, we added mixture modeling features that I have alluded to before, with significant speed improvements for mixture models with multiple latent class variables, which are more computationally demanding. So that's very handy for latent transition analysis and random intercept latent transition analysis. And like we said earlier, the output has been substantially simplified for cases with multiple latent class variables. Now, Bayesian analysis is also quite relevant here, and we have made significant speed improvements for Bayesian computations using this new parallelized computing approach, which recommendation is to say processors equal 8 to get faster computations to benefit from that development. And we have also made Bayesian estimation of 2-level models with latent variable interactions using the X-width option. So we have a Bayesian alternative to ML, because ML gets into too high-dimensional integration to handle that for realistic sized models. And Bayesian fit statistics have been added in 3 areas: improved posterior predictive p-values when they're missing data, and Bayesian versions of CFI, TLI, and RMSEA, including confidence intervals, which you get easily through Bayes, and a Bayesian version, and this is interesting, Bayesian version of the wall test that you have in model test for ML. It's a Bayesian version of that to test parameter restriction. So that's a way of testing nested models, restricting a number of parameters to see if they are really necessary. Finally, then, on slide 80, I just listed the recent Mplus related papers that we've been relating to. This paper is a technical report that's on our website. It has to do with the improvement in maximum likelihood mixture modeling, speed, and then the Bayes improvement in time, the parallel computations, they're described in this technical report. And then a couple of new papers. This is Bayesian estimation with latent variable interactions that I just mentioned. It's coming out in structural equation modeling. And then Advances in Bayesian model fit evaluation, also coming out in structural equation modeling. And the paper that's already come out last year, latent variable centering, that is how you can do better than centering by observed group means, and instead do latent variable centering, even in multi-level and in time series models. And another general paper comparing different kinds of models for the analysis of intensive longitudinal data, long longitudinal data. And then finally, this paper, which is coming out in Psychological Methods, I do believe. We'll get through the review. And the paper that's the impetus for this web talk. So that's the paper that made me think about all of these different related topics for this web talk. So the paper is based on an idea that came to mind during a morning walk that I took in January 2019.